This is Chemistry Podcast 8.5, and we are going to talk about partial pressures, what they are, and also how you can calculate them. So the first thing is John Dalton came up with the law of partial pressures, and it says that for a mixture of gases in a container, the total pressure that is exerted is the sum of the pressures of each gas, their individual pressures. So what we can do is we can look at if we have a mixture of gases and we know their individual partial pressures or how much pressure each gas exerts on its own, then we can add those up and we can get the total pressure of the new mixture in the container. So there are three different types of partial pressure problems, and the first type is as simple as finding the total pressure by adding each of the individual pressures of each gas. So the total pressure is equal to the pressure of the first gas plus the pressure of the second gas, and then so on for however many gases you have. There's a picture here that kind of illustrates this. We have oxygen gas and nitrogen gas, and you can see that their pressures are right here. So the oxygen is 200 torr, the nitrogen has a pressure of 330 torr. If we were to take those two gases and mix them together in the same container, what we would see then is that the total pressure would be 530 torr. It would be the sum of their individual pressures together. So adding up the individual pressures of each gas gets you the total pressure. Our example problem here for a type 1 says a tank contains 9.3 atmospheres of helium and an unknown pressure of oxygen gas. If the total pressure inside the container is 11.7 atmospheres, what is the partial pressure of the oxygen gas? So what we're going to do is that first law that we just wrote down, that the total pressure, and in this case it must be equal to the pressure of the oxygen plus the pressure of the helium, because those are the two gases that are in this mixture. So I have oxygen and helium. They told me the total is 11.7, and we'll say ATM, and they told me that the helium is 9.3. So what we're looking for is what is this leftover that must be the oxygen to get us to the total. So all you have to do for this one is take 11.7 and subtract 9.3 to find the difference. You find that it's 2.4 ATMs is the partial pressure of the oxygen. So if we summed up 9.3 plus 2.4, we're going to get the total of 11.7. All right, the next type is where we're going to use mole fractions in partial pressures. And a mole fraction we haven't talked about before, but a mole fraction is a ratio, and it's the ratio of the number of moles of a given compound in a mixture to the total number of moles in that mixture. It's sort of like we're doing percent composition, but we're not doing the percent part. So you're going to take the moles of whatever you're looking at and you're going to divide it by the total moles of the compound. You're just not going to multiply by 100. So if we wanted to write a general equation for mole fraction is abbreviated, or the variable we use is chi, and it's this kind of weird looking x. So the mole fraction of whatever compound I'm focusing on is equal to the moles of that compound, however many we have, divided by the total moles in our mixture. So we're going to use this because of the ideal gas law. We know that moles and partial pressure are directly related. So from the ideal gas law, the number of moles of gas and the pressure are directly proportional. We know as one goes up, the other goes up. As you add more moles of a gas, the pressure is also going to increase. And the partial pressure of an individual gas in a mixture is the mole fraction of that component times the total pressure. And that sounds confusing, so we're going to write a little formula here. So if we're looking for the partial pressure of some gas in a mixture, what we can do is we can take the mole fraction of that gas and multiply it by the total pressure. And we'll be able to then, from that, figure out what the partial pressure of the gas is. So we take the mole fraction of the gas and we multiply by the total pressure to get the partial pressure of whatever gas we're focusing on. And here's our example problem. A gaseous mixture contains 2 moles of oxygen gas and 3 moles of nitrogen gas. If the total pressure of the mixture is 10 ATMs, what is the partial pressure of each gas? So because they've given me moles of nitrogen gas and moles of oxygen gas, The first thing I'm going to do is figure out the mole fraction of oxygen and the mole fraction of nitrogen. So to do this, I take the moles of whichever gas I'm looking at on top and I divide it by the total moles. So the mole fraction for the oxygen is going to be 2 moles of oxygen on top divided by the total, and 2 plus 3 is 5. So if I take 2 and I divide by 5, I get 0.4. Do not change that into a percentage, and you can see your units go away. So this is now just a number. I'm going to do the same thing for the nitrogen. Nitrogen was 3 moles, and it's still a total of 5. So when I divide those, I get 0.6. Now what I can do to figure out the partial pressure is use that equation that we just wrote down. So the partial pressure of oxygen is going to be equal to its mole fraction, which is 0.4, and I multiply it by the total, which is 10 atm. That's 10 atm for the total pressure of the mixture. 0.4 times 10 equals 4 atms. So the oxygen has a partial pressure of 4 atmospheres. The partial pressure of nitrogen must be 10 minus 4, whatever is left over, or you just plug it in the same way, this time using 0.6 times the total pressure. That's going to equal 6 atm. So the partial pressure of the oxygen is 4 atmospheres, and the partial pressure of the nitrogen is 6 atmospheres. And we can check that we did that correctly because 4 plus 6 is 10, which is what the total must be. All right, the last type of partial pressure problem you'll see is one where we collect a gas over water. And when we're collecting a gas over water, like in this setup right here, what we find is this gas that's getting collected right here, because it's displacing the water and we're collecting this gas. This is whatever gas we have and water vapor. Because the gas is bubbling through water, some of that water is going to escape into the gas phase and we're going to get water vapor mixed in with our gas up here. So in order to find the pressure of what they call the dry gas is meaning without water, we take the pressure total that we know and we subtract out the pressure of the water vapor. And the pressure of the water vapor is found on your green paper that you have, the green paper of partial pressures. So it's found on the green chart, and you look it up by the temperature. So if we were collecting gas and the temperature of the water was 25 degrees Celsius, you would go to where it says 25 degrees Celsius on that green paper, and you would look for the water vapor pressure that they give you. So this is the chart that I was talking about that you're going to use. For example, if it's 3 degrees Celsius, you could use it in kilopascals, atmospheres, or torr. It's all here for you. So make sure you choose the correct one. Here's our example problem. It says I have 0.650 liters of oxygen gas that were collected over water at 22 degrees Celsius and a pressure of 754 torr. Calculate the moles of oxygen gas that were collected. Well, the first thing, I know I'm going to have to use PV equals nRT to calculate the moles. So that's what I'm going to be looking for. I know the temperature. The temperature is 22, but I want to convert it to Kelvin, so I'm going to add 273. So that's going to become 295. R I can pick out based on torr. I'm going to use the millimeters of mercury one, so 62.36. The pressure, though, is where I need to watch out. So my total pressure is 754. That's with the water and the oxygen gas. I need to subtract out the water. So you're going to go to that green paper and you're going to go to where it says 22 degrees Celsius, and we're going to see that the vapor pressure of water at 22 degrees Celsius is 19.83 torr. All you do is subtract out the water vapor pressure from your total. So 754 minus 19.83, that gets you 734.17 torr. And that we would say is of the dry gas, is of the dry oxygen. So this is the pressure that we're going to use when we plug it into PV equals nRT, And we have our V right here already in our problem. So all I'm going to do is just plug this in. So I have 734.17 torr, what I just found for my pressure, times my volume in liters, equals N, which is what I'm trying to find. My R is 62.36. I chose that one because torr and millimeters of mercury are the same thing, and that's the R that goes with those. And then my temperature in Kelvin is 295. I do all that and I solve for moles, and we end up finding 0.026 moles of oxygen gas. So just making sure when we collect things over water that we use that green sheet to account for the water vapor pressure that's going to be with that gas. Okay, so that is it. You need to know the 3 different types and how to calculate partial pressures with each of them. Make sure you have your green sheet so that you can look up the water vapor pressure for each of those, and also make sure you can calculate mole fractions, since that's a new type of calculation that we're just dealing with right now. So that's it, and we will do more practice in class.